Group two. Tamisha, Pete, it's in-house. All right.
Okay.
And Mindy from group 10.
Group 10. Mandy is in the house.
Did you
Welcome.
get Kimberly from group 10? Did you get Chanel Marshall for group 2?
What group, Kimberly?
Kimberly, group 10.
Group 10. Kimberly's in the house.
Okay. Did you get Chanel Marshall for group 2? Just because I've said it a few times.
Okay, group two.
Yeah.
Chanel Marshall. Yes, Chanel is in the house.
Professor.
Yeah.
Thank you.
Rika Camille Teal, group 9.
Group nine. Let's see.
Rika Camille.
Camille. Group 9, right?
Yes.
All right. Camille's in the house.
Alexa Gallardo from group 9.
Who?
Alexa Gallardo.
Alyssa. Okay. Yes. Alyssa.
Hi, Professor.
Welcome.
Thank you.
Professor.
Yes.
This is Mercury from group 3.
Group 3. Mercury from group 3.
Mercury Edwards.
Okay.
This is Estella from group 4.
Group 4. So, welcome, Mercury. Welcome. That's group 4, Estella.
Yeah.
Estella is in the house.
This is Anakin from group 9.
Group 9. And this is who?
Anakin Paez.
Okay.
Professor.
Hi, Anakin. In
Yes.
the house. Yes.
Professor.
Yeah.
This is Jennifer Cervantes.
Uh-huh.
I emailed you regarding about the groups because I wasn't on the list for any groups.
What group? So you don't. Who you been working with?
I've been working with my lab group, but they showed me the
What's the lab
List?
group? Oh, wait.
on
What is
group
it?
1.
The class roster group. You in group 1?
No, for lab I'm in group 1, but for your lecture class.
This is a class roster.
Oh, okay, but regardless, I've been emailing you about the groups because I wasn't on the list for any group.
Really?
Yeah.
Oh my goodness. Let me see. I don't know. Maybe I can put it in a group. I got group 10 got 6 people in there. Group 8 has 6 people in there. Group 7 got 5. Group 6 got 6 people in there. Just like one group I can put you in, one of the groups.
Well, whatever group you want to put me in is fine.
Okay, let's see. Put it in group 7 then.
Okay, thank you.
So give me her name again.
Jennifer Cervantes,
Jennifer, J-E.
NNIFER,
Okay.
Cervantes,
Spell that.
CERVANTES.
Is it Z
C,
or C?
yeah.
C-E-R?
VANTES.
C-E-R-B-A-N-A-N?
Yes,
Mm-hmm.
NTES.
T-E-S?
Yes.
Okay, so you're in group 7 now.
Okay, thank
Look
you.
for them, okay?
Okay, thank you.
All right.
Professor,
Yeah?
are you taking roll call?
Yeah. I'm going to
Okay,
be doing
this is-
that for now.
Oh, okay. This is Robin Penalonso from group 4.
Group 4. Robin is in the house. All
Yeah,
right.
I don't know if you did that in the past 2 meetings. I
Oh, no,
didn't
no.
check
This
in,
is
but-
the first time doing this.
Okay, perfect. Thank you.
Yeah. Mhm.
Professor,
Yeah?
this is Christy Gutierrez from Group 3.
Group 3. Christine, group 3.
Professor,
Yes, sir. Let me finish with Christine.
I
Group
also
three.
had another.
No,
This is
Christy
Christy.
Arusi. Oh, good. Oh, yeah. Okay. I got you.
I also have a question. I
Yeah.
know I got an email saying that for Group 5, there's supposed to be Citlali Niebla. I had already sent you the final list of the groups, the revised one, and she is included in it. And they're saying that you said she's not in the group.
What, for, who's this person?
Citlali Niebla, group 5.
Group 5?
Mm-mm.
No, I just put her name there.
So she's there?
I just put her name in group 5, yeah.
Okay, thank you. Just
Yeah.
want to verify.
All right. Okay.
Professor,
Mm-hmm.
this is Yara Bancola from Group 7.
Group 7. Sierra. Yeah. Sierra's in the house. Yeah. Group 7.
Okay, thank you.
Mhm.
Professor,
Yeah.
this is Aglaya from Group 5.
Group 5. Who now?
Aglaya Diana Brillantes.
Okay. Aglaya?
Yes.
Okay, you in the house. Yeah. 5.
Professor Anna Bernal, Group 3.
Group 3.
Group 3, Anna Bernal.
Anna Bernal is in the house. All right.
Professor,
Yeah.
this is Jose from Group 7.
Group 7. Group 7. Jose, you in the house.
Professor,
Uh-huh.
this is Maria Clemente from Group 8.
Group 8. Maria
Clemente.
in the house. All right. Uh-huh. Keep going.
I'll text you her number.
Hi, I'm Christine Hernandez from Group 8.
Group 8, Christian Hernandez.
Mm-hmm.
Yes, you're in the house.
Hey, thank you.
Welcome.
This is Nathan from Group 9.
Group 9. Nathan, you're in the house. Welcome.
This is Dorothy Lautoa from Group 3.
Group 3. This is who?
Dorothy.
Yeah. Dorothy, you're in the house. All right.
Hi, Professor.
How are you?
I am good. My name is Sasiton Unskon. I'm from Group 9.
Group 9. You what? Say that again.
Sasiton Unskon.
Okay, all right. You're in the house. Welcome.
Thank you.
This is Anna Ocampo from Group 8.
Group 8. You're in the house. Welcome.
Professor, this is Haley from Group 8.
Group 8. Haley, you're in the house. Welcome.
Group 7, Rosa.
Rosa, you're in the house. Welcome. Okay, I got auto group 1. I got auto group 6. I got auto group 10. Missing one person in group 9. Christiana. Group 9.
There's Christiana Tello, Group 5.
Group 5, Christiana Tello. Yes, you're in the house. All right. Anybody else missing?
Good morning.
Money, how are you?
I am well. How are you?
Oh, yeah. Praise the Lord. Yeah.
Praise the Lord. That is right.
That's right.
My name is Janelle Green. I'm in Group 2, right? Group 2.
Group 2. Janelle Green is in the house.
Yes, sir.
Welcome. All right. Okay. I got 2 people missing in group 2. Whitlock and Stevens. All right. Auto group 1 is accounted for. Group 2 missing. Group 3. I got 1 person missing in group 3. Group 4. I have 2 people missing in group 4. Bro and Velasco. and Andrina. And group 5, I got
Hello, Professor. I'm here. Adriana Velasco for group 4.
Group 4 in Sinahao. Welcome.
Thank you.
All right. Group 5. I got everybody accounted for in group 5. Got everybody accounted for in group 6. I got everybody accounted for in group 7. Everybody accounted for in group 8. Group 9, I got missing one person. Christina Beluson. I'm missing from group 9. All accounted for in group 10. Very good. Now we can begin. So this is what we'll do every morning, okay? All right. So today we're going to do chapter 10. Tomorrow is chapter 11. Our last chapter before the exam. And then Thursday, you just spend that time studying. And then you take your study exam. All right, so we deal with gases. Okay. Yeah.
Like the exam is what day, just so I could write it down.
It's only, I think it's only thing in syllabus. You see, do you have a syllabus?
I'll open it right now.
All right. I think it starts on the 30th.
Okay.
Yeah. Okay, so we know huh? Oh no, the last day you can last day is the last day you take it that they close at midnight. Mm-hmm. So this is chemistry, studying matter and the composition of matter. And we said matter has different states. We're only dealing with 3 states right now: liquid, solid, and gases. Tomorrow we'll be doing liquids and solid. But today we do gases. All right, these are the states. And then we see these states in a chemical reaction. And so therefore we begin with, there are 5 important properties of gases. Properties are so important in the study of anything. What causes something to behave the way it does? It has something unique, something special in it that causes that behavior. And that something is called property. So if you don't have that property, you can't behave that way. So it's so important. 5 important properties of gases that cause anything to be classified as a gas to behave like a gas. Number 1, gases have a variable shape and volume. Variable meaning, like if we took mathematical algebra, we say X and Y, Z, those are variables that you solve for in the problem. So that means that it's something that, you look forward to finding. Gases expand uniformly, all right? We just did a gas experiment where the rubber ball was, comparing gases with spring. That was interesting. Spring, you probably never thought of that. Expand uniformly in a uniform fashion. When they expand, one part of it does not stay behind, other one stay ahead, and they all go together. The compression is uniform. The expansion is uniform. That's that property that gas got that. Gases have a low density. Lower density, which is mass per unit volume. And so for gases, it's very low. They have that as a matter. Gases mix uniformly with other in the same container, uniform. A whole lot of things about gases are uniform. They do things together. I hope we could do stuff together like that. We'll have less problem. Uniform, doing things together with no confusion. Everything just beautiful. Everybody having fun. See, gases have fun. They do things together. And they, and they're singing, they're dancing, they're doing everything, they're having fun. We should do that too. Let's take a closer look at these properties. Now we're going to look at these properties. All right. Property number 1. Gases have a variable shape and volume. A gas takes a shape of its container. Whatever container you put it in, it will take the shape of that container. Filling it completely. They always fill it completely. If the container changes shape, the gas also, they work well together. We do things together. Whatever happens here, we're all gonna respond to that. So now, if ever in America wear mask, that uniformly they will behave like gases. But some people wear masks, some people don't want to wear. Some people don't want to obey this rule. See, that's why we're not gases. We're having problems. But gases, they do things together. Yeah, they work together. See? So therefore, they don't have that much problem. Gases expand uniformly again. When they're going to expand, they're going to do it together. The volume of a gas decreases when the volume of its container decreases. If the volume is reduced enough, the gas will liquefy. So we can liquefy in the chemical industry, the chemical engineering. When we hear liquefied gas, we reduce it, because the gas particles are so far away from each other. All right. But so when you bring them closer, they become liquid. This is how we liquefy gases. But as long as they're out there having fun, you cannot liquefy them because they're in that form. But the closer they get together, then we have that liquefied gas. Gas is compressed uniformly. Compression, just pressing stuff together like it has sponge. Put sponge in your hand and you squeeze that sponge, you compress it, okay? And a gas constantly expands to fill a sealed container. The volume of a gas increases if there is an increase in the volume of the container. So gases have a low density. Density is so low, all right? The density of air. Air is a mixture of gases. Talking about mixture, air is a mixture of gases. The two major components of air will be nitrogen and oxygen. There are other gases there, but in small amount. The density of air is about 0.001 gram per milliliter. That is so small. That is 1 × 10⁻³ power, if you put it in a scientific notation. Compared to a density of 1.0 gram per milliliter for water. Water is 1.0. So water is way denser than the air. Air is about 1,000 times less dense than water. 1,000 times. That's right. All right. So gases mix uniformly. When you mix them together, they mix well, no confusion. And you don't hear any molecule say, "Oh no, go with it. You stay with it." No. No, they mix well together. They hug each other. They're having fun. With other gases in the same container, they have a conversation. They're having fun. Air is an example of a mixture of gases. When automobiles emit nitrogen oxide gases into the atmosphere, they mix with the other atmospheric gases. They mix well. The mixture of gases in the sea container will mix to form what we call a homogeneous mixture. So the mixture is homogeneous. Once there's no line of demarcation, there's no separation to identify who's who, who's what, that is homogeneous. All right. So now, greenhouse effect. You heard that before. Greenhouse effect, people say that. But have you ever asked them, what is greenhouse effect? I hear that all the time. Greenhouse effect, greenhouse effect. What is it? Several gases contribute to the greenhouse effect. So in their 5 properties, they make contribution to greenhouse effect. All right. High energy radiation strikes the Earth's surface and is converted to heat. All right. Heat, which is a form of energy. All right. This heat is radiated from the surface as infrared radiation. I mean, you have the spectrum. We talked about spectrum before. The visible spectrum, what is above and what is below visible. We say what? From 400 nanometer to 7 nanometer, that's visible. anything above that, below that, we cannot deal with. We can't. So therefore, we have radiation. This infrared radiation is absorbed by the gases, all right, and released as heat in all directions. That's what we're looking at right now. You know, the gases will absorb that radiation and they release it as heat, all right, heating the atmosphere. So that cause, when they release that heat got to go someplace. So the atmosphere is above us, you know, at different levels of atmosphere. So that we have is going there. No, stratosphere, all the places. Now, gas pressure is a result of constantly moving gas molecules striking the inside surface of their container. So when they're in the container, they're moving around, striking the container, you know. So pressure is force divided by area. Pressure P is F over A. That's what the gases are doing. F over A, F over A, F over A, all in our container, F over A. Then they create pressure. The more often the molecules collide with the size of the container, making F over A, the higher the pressure. The more often. So therefore, if the F over A is getting very frequent, force divided by unit area, which is high pressure, then you know the higher the temperature, the faster the gas molecules will move. So temperature has something to do with the movement, you know, causing them to move faster. All right? So just like if you were in a heated place, you move faster. All right. So we see higher temperature, higher pressure. All right? Because why? The pressure is high because there's more collision going on, more hitting going on because of that, the high temperature. So F over A, F over A, F over A, P equal to F over A is happening frequently. Lower temperature, then gas begin to relax. So there's less F over A. Less F over A. So you know, the gas get kind of weak and tired, moving slowly. All right. So atmospheric pressure. The atmosphere exerted pressure, F over A, is a result of the air molecules in the environment. All right? Evangelist Torricelli, he invented a barometer. So normally in a typical chemistry lab, when you get into the chemistry lab, on the side of one of the walls, you see the barometer. So you got to check what is the pressure in this room before I start my experiment. But in the 1643, it was a very good year, measure atmospheric pressure. So look what he was doing. He had a mercury in there, in an open container. He had a mercury in the tube. All right, and so therefore, when that pressure touched that mercury, what happened? Well, the mercury in the tube will move back up and down. So this is what he was doing, you know. During those days, this guy didn't have any cell phone, no TV, none of these things that you have today. So they were not distracted. But today it's very difficult to learn. So it's hard to learn because there's so much distraction. These guys were able to do a lot. They were not distracted. All day long, they were doing something, you know. But today, oh boy. All right. So standard pressure is the atmospheric pressure at sea level. Sea level meaning, all right, you go to the, what do we have in California? Pacific Ocean. Level of that, right above that, inches of mercury. So here is standard pressure expressed in other units. So now let's take a look. There were 10.1 units of gas pressure. Atmosphere, we hear ATM. Oh, ATM, you know what an ATM also stands for, right? Our time when we hear ATM, we're thinking about going to the bank, the machine on the outside of the bank, and we're gonna get some money out. You gotta be very careful. Look around before you do that. All right, so we have ATM, inches of mercury, which is you take out a little ruler and measure it, 29.9 inches, that mercury in that container, 29.9 inches. Centimeters of mercury. Now we can convert the inches, 2.54 centimeter equal to 1 inch, so we can do the conversion there. For 1 unit, the inches is the English units, centimeter is SI. So millimeters of mercury, mm, that's the smallest unit, all right? So we know that 10 mm, you got 1 centimeter, so we can convert that. If you multiply 76 by 10, you get 760. So the relationship between cm and mm is based on the fact that you got 10 mm equal to 1 cm. All right. So now we give him credit because he was doing an experiment. So we say 760 is also 760 of mercury is the same as 760 of Torricelli, that Italian guy. All right. So pounds per square inch. That's the English. But most people out in the street are familiar with 14.7 psi. PSI, pound per square inch. What is the PSI? When you put air in your tire, and you see PSI there, because that's something. I mean, pound per square. How many PSI can get in your tire? Or you can, and then you can deflect it if it's too much PSI there, you know. So then kilopascal. Now, chemical engineers, you know, do work in kilopascal. All right. So we see here comes the problem now. Same concept of problem solving. We'll follow you throughout this course. We're almost there. Just bear with me. I love you all so much, but bear with me. We'll get there soon. I'm taking you there. We'll soon hang it up, and you'll be dancing around because you've done what? 6 weeks of work with me. I torture you so much. Ooh, what a torture! You said Dr. Tuku, he's a torturer. All right. The barometric pressure is 26.2 inch mercury. What is the barometric pressure in atmosphere? So what do we want? We want atmosphere. You can put a sign up in the street. We want atmosphere. We want atmosphere. We want atmosphere. In Hg. So we say, you want atmosphere is 29.9 inches of mercury. So we can write a unit factor. So we can write 2 unit factor, 1 ATM over 29.9 inch or 29.9 inch over 1 ATM. So that unit factor is there. Based on the starting point, we're given what? 26.2 inches of mercury? Yes, we're given that. That's the beginning part. So now the 2 factors we wrote, we'll now look at which factor will drop the inch mercury. Each mercury cancels from each mercury. You got to make sure you pick the correct factor for that to happen. Because what do we want? We want atmosphere. We just had a sign up in the street. We want atmosphere. Atmosphere. We want atmosphere. So now you got atmosphere. All right. So we see there are 3 variables that affect gas pressure. Okay. We said pressure is what? Pressure P equal to F over A, F over A, F over A, F over A. All right. So we have that. What is it? Variables. Something that is subject to change. Variable A, you know, like you solve the problem in algebra, you say, what is X? What is Y? What is Z? So those are the variables because they are subject to changing. They're not constant. Constant means always the same. So a variable is something that is subject to change. So therefore, the volume of a container is subject to change. Temperature of the gas, subject to change. Number of molecules of gas in the container. All right. So all those things will affect gas pressure. Will affect gas pressure. So bear in mind. All right. So we see now, when volume decreases, we decrease the volume, everything, you know, gas do things in uniform. When the volume decreases, the gas molecules collide with the container more often. So pressure increases. So when the volume, when you decrease the volume, what happens? So now the gas, they get so close, they can hit the thing, you know, faster. All right. So pressure will increase. But when you increase the volume, they're so far away from each other, it takes a long time to hit something. Long time to hit. All right. When you decrease the volume, what happens? They hit faster. F over A, F over A, F over A, F over A. When volume increases, the gas molecules collide with the container less often. So now you got more room. More room. You know, we're doing what? We're distancing from each other right now, right? So we increase the volume. So just everybody stay away from each other. All right. So that's what we're doing right now. So therefore there's no contact. So collide with the continuum less often. So less often you come in contact, just like being in an elevator. If 3 people on an elevator that takes 50 people, 3 people, that's still, you know, they're not going to touch one another. If anybody on an elevator of 50 people, 3 people on there, anybody touch you, they you know, watch it, they asking for a problem. They got no reason to touch you because just 3 people there. But when you start getting 49, and people start getting so close to each other, when somebody touch you, you don't mind because you know you got more people on the elevator. But there's no reason for 3 people on a 50 people elevator to touch somebody. That person there is no good. The person is looking for trouble. All right. So therefore, that's the same thing happening here. When temperature decreases, the gas molecules move slow and collide with the continuum less often, so pressure decreases. Because temperature decreases. Temperature and the pressure, they do stuff together. When temperature increases, the gas molecule move faster and collide with a continuum more often. So what happened to the pressure? Pressure F over A will increase. P equal to F over A will increase. So these are things we're talking about what? Matter, anything that occupies space, has weight. Chemistry deals with the study of matter, and matter has 3 states: gases, liquid, and solid. We are featuring gases today. Tomorrow, we'll be doing liquid and solid together. All right. So we see here, when the number of molecules decreases, there are fewer gas molecules colliding with the side of the continuum, so pressure decreases. When the number of molecules increases, there are more gas molecules colliding. Collision, in all chemical reactions, it's all about collision. All about collision. Collision that you're not gonna sue somebody for, you're not gonna pay for. If collision don't take place, then nothing works. All right. So with the side of the continuum, so pressure will increase. F over A. F over A. Remember that. Rubber boy. So everybody was doing something. Terracella, he did his stuff. Everybody was trying to say, I heard that Terracella did something. Well, I want to do mine too. What am I going to do? So what did Robert do? Robert got a J2. You know, that tube in the form of J, using liquid mercury. Again, mercury. He found that the volume of air decreased as he added more mercury. You see that? The volume of air, the air will decrease as he added more mercury. He said, hey, this is interesting. When he half the volume, the pressure double. Oh my goodness. So now they're not going together. So Robert Boy is dealing with what? Pressure and the volume, keeping the temperature constant. The temperature, you go out there, I don't need you here. You stay there, be constant, all right? Let pressure and volume be the variable here, the change unit. So he kept doing it, he kept looking. He said, when we halve the volume, make the, start with the volume, what happened? The pressure will double. This is interesting. So he was working with it. All right. So now, boss, he formulated a law. After theory, the next thing is law. Bohr's law says what? That the volume of a gas is inversely, that means they're not going together. They're not going to be inversely proportional to the pressure at a constant. What is the proportion? Proportion is with 2 equal ratios. These 2 ratios here do not go together. So therefore, the pressure to the pressure at constant temperature. So look at the graph. Very interesting graph. Pressure, volume. For the experiment you did, you should have a graph like that. Inversely proportional means 2 variables have a reciprocal relationship. 2 variables have reciprocal relationship. All right. So today you buy somebody lunch today. All right, you buy your best friend take them to lunch. So tomorrow, your friend's supposed to take you. That's reciprocating. All right. So it's not just you buying lunch, they just keep eating. Reciprocating. So when you do that, I do that today, you do that tomorrow, and so on. So reciprocating relationship. Mathematically, how do we express it? We say volume is directly proportional to 1 over F over A. That P, when you see P, start thinking F over A. We can substitute that P for F over A. So P equal to F over A. So 1 over P over A. Reciprocation. That is the graph. Pressure, volume, with temperature being constant. That graph is high. So when you look at the graph here, way up here, now here's why it's so interesting. When you look up here, the last point where high pressure, okay? High pressure, what happened to the volume? Look at it, come down there. You see that zero line? The volume that we drop that line down here, that volume is pretty close to zero. Do you see that? It's very close to zero. You see? All right? So now, if I pick a point from here and come down here, every time I pick a point on a graph and going away from zero, what happened? I'm increasing the volume. What happened to the pressure? Pressure is getting smaller and smaller. This is a very interesting graph. So low pressure, high volume. So the last point over here, away from that zero, you got a high volume there, the pressure is very low. So what you do, take a point, draw a line going toward a pressure line, and you see how low the pressure is. If you pick a point from the top there, drop the line down, and you see, so that this is how you, so if we're in a setting, I will give you a graph like this and say, okay, given the following pressure, find the volume. Given the following volume, find the pressure. And I will have you pick a point, find that point, and you look at that pressure or the volume. So this is why graphs are very, very important. You know, you can do a lot of graph. In science, we do a lot of graphing. Because graph, you can just go on a graph and pick information from a graph. So that's how you read that. So the last point up here, way up here, you look at me. So therefore, I drop it down, see how close it is to zero. All right. So if we introduce a proportionality, so constant, proportionality constant, in place of that proportion, to put K there, we can write Boyle's law as what? V is equal to K times 1 over P. Go back. We take this proportionality, V is proportional to 1 over, so remove that, move that there, and I put constant there, then look what we got. So therefore, we can also rearrange it to say PV is equal to K, meaning PV is equal to constant. All right. So you know that everyone was trying to do something with gases. Gas is so interesting to study. The properties that were outlined, Albert read this property, studied properties. You know what? I want to do something. So Boyle is doing something. So Boyle said, okay, in my case, I'm going to make temperature constant because this is the whole study is about PVTN, the N7 Avogadro's number molecule. So PVT study. This is all the PVT study, keeping some constant. So Boyle said, I'm going to keep temperature, hold temperature, don't move temperature, just sit right there. Temperature is like right now, in Boyle's case, temperature is like a kid. Don't move. All right. Let's take a sample of gas at P1 and V1 and change the conditions to P2 and V2. Because the product of the, now go back to that graph. Went back to that graph. Let's go back to that graph. See the graph here? You see that curve like that? When you have a product, you have a graph look like this. PV, meaning pressure times volume. That's whenever we have a product, you have a graph hyperbola. This is a hyperbola. This is what you get. like a satellite dish on top of your house. So you see, the graph looks like that when you have a product. PV, anytime you multiply two things, you have a curve like this, like this. All right. So now we say PV, P1, V1, equal to the constant. So it's P2, V2 equal to constant as well. Okay, so now in this case, you got to know three things to find the fourth one. All right, in Ball's case. Here's the problem. To find a new pressure after a change in volume, based on our graph I just showed you, to find a new constant, what do? All right, just a second. Let me take a sip of water here. Take a little break. You take 1, 2. Take a sip of water. How about take a sip of water? All right. All right, I'm back. So V1 time, so we have a factor P1 over P2 is a factor. So therefore, volume 1 times pressure 1 times pressure 2 over pressure 2 equal to what we are about to find. So this is the pressure factor right here. P1 over P2, that's the pressure factor. To find a new volume after a change in pressure, so therefore now we say so now we have a volume factor as well. P1 over V2 is a volume factor. P1 over P2 pressure factor. So therefore we found the new pressure. So this is what Ball was doing. Now here's the problem now. A 3.50 liter, we said it.
Can you go to the previous slide, please?
Go back?
Yes, just one.
This one right here?
No, the one right after. Was that one right after? Yeah, right there.
Right there?
Yeah.
Okay.
Okay, thank you.
All right. So the problem is, the volume here is gas are measured in liter. We'll talk about that, making that connection from previous study. So 3.50 liter sample of methane gas exerts a pressure through the process of collision, hitting things here and there, of 1550 mm of mercury. All right. What is the final pressure if the volume changes to 7.00 liter? Take a look at the two volumes. What is happening? What do you think? You start with 3.50 liter. Now you end up with 7.00 liter. What do you think happened there? What happened to the pressure? Based on the graph I show you. So what? Can somebody tell me what happened to the pressure there?
Is it decreasing?
Exactly. Volume is going up because they don't go simultaneously. One goes up, one goes down. All right. So therefore, pressure will go down. So therefore, we see there, when you look at the problem, you got what, 775 mm of mercury as a new pressure, and you started. So therefore, we got. We started with 1550 mm of mercury, right? It went down to what? 775. It went down considerably. The volume increased and the pressure decreased as we expected. So just by looking at the problem before you even solve the problem, follow the concept of Boyle's law. One goes up, one goes down. One goes up, one goes down. So take a look at a number before you even start the problem so you predict what to expect. That's one way to know what are you going to get. You're doing something right. Okay. So Robert Boyle spoke Latin and Greek. Good for him. By the age of 8. Isn't that something? Latin and Greek. Enrolled at Oxford University at age 27. That's in England now. Designed a vacuum pump. Vacuum means negative pressure. The pressure is absent there in a vacuum. All right. So designed a vacuum pump in 1657 and used it to prove sound does not travel in the absence of air. So when you hear vacuum, it's the absence of air, right? All right. So publish the findings in 661, arguing that theories were only as good that the experiment were based on. All right. So he did that. He's not here. So now we come. So we talk about Torricelli, we talk about Boyd. Everybody was trying to do something with the gas. So Jacques, that's James for in French. Jacques Charles. He said, well, you know what? I found out what Torricelli did. I found out what Boyd did. Now I'm going to see what I can do. We all try to work with the PVTN. So in Charles' case, he said, well, this time I'm going to do what? What am I going to do? I'm going to keep pressure. I'm going to act pressure to sit down. F over A, you need to sit down this time, all right? You sit down and let me deal with the temperature and let me do the volume. All right, so pressure said, okay, I'm going to sit down. I'll wait. So therefore, he said, so now you see now, when you have a product, we say PV, you have a curve, that hyperbola. Keep that in mind, that graph in mind. Whenever you have a quotient meaning division, all right, fraction, you always have a straight line. This is one way you can determine what a line is going to look like before you even started. When you have something divided by something, it's going to be a straight line. Something times something is going to be a curve. That information is very, very important. Make note of that. So when you see a curve like that, you already know that something is multiplying by something. When you see a straight line, you know something is divided by something. All right. You know, so we say, so Charles' law. So now he said, so volume is what? Directly proportional to temperature. When something is directly proportional to something, they go together. When you make a move, I make a move. When you make a move, when you don't make a move, I don't make a move. All right? Note that Charles' law gives a straight line graph. Straight line graph meaning something divided by something. Boys, something times something, curve. Keep that in mind. All right. We can write Charles' law as an equation using a proportionality constant K. You need a K. All right, so therefore V is equal to KT. V is equal to KT. How do you solve for K? Divide both sides by T to solve for K. So V over T, see now, you see the quotient, you see the fraction. That fraction, whenever you have a fraction, you are bound to have a what? Straight line. Bound to have a straight line. All right, so keep that in mind. Again, let's consider a sample of gas, a V1 and T1, and change the volume and temperature to V2 and T2 because the ratio of the volume to temperature is constant. We can write. So now we can say V1 over T1 is equal to V2 over T2. So in this case, the easiest way to solve this problem is to cross multiply. So when you cross multiply, you have what? V1 times T2 is equal to V2 times T1. In solving these problems, this is the easier way to deal with the situation. You have two quotients like that, two fractions like that. Cross multiply them. All right. So below is an illustration of Charles' law. Now, let me tell you about the scientific community. They're very, very technical. And we talk about the IUPAC people, you know, the top. You gotta show proof that what you're trying to communicate is what it is. We saw what Boyd had to show proof. So now Charles is going to also demonstrate why he thinks that the volume and the temperature, you know, will go together and pressure will be constant. So as the balloon is cooled from room temperature, what is room temperature? 20 to 25 degrees Celsius is room temperature. As the balloon is cooled from room temperature with liquid nitrogen, you know, have you ever heard of cryogenic? You know, you put something in there, it's gonna, when you get it out, it's just fresh as ever. All right. So that means the liquid nitrogen has a temperature of negative 1.96 degrees C. Very, very cold. Very cold. Negative 1.9. So what happened? He put air in the balloon, put it in liquid nitrogen. Look at the balloon. Look at what's happening. What happened to the volume? Volume is going down. As the temperature is going down, volume, you see they going together? Hi. He said, I got something. I got something to show. Now I can convince my fellow scientists that when the volume goes down, temperature is going down too. Isn't that something? Everybody was trying to make contribution to gases. Bohr did his thing, where he said pressure and volume. When the pressure goes up, the volume goes down. When the volume goes up, pressure goes. No, he did that. He made a demonstration. So Charles said, okay, all right, I got it. I got something else. I'm going to do mine. So you see. So to convince the scientists of anything, you got to show proof mathematically. You got to do it in an experiment and prove it. So this is what he's doing. All right. So you see the balloon. See the balloon there. The balloon. The volume is going down, and you know the temperature is going down. So here we go. To find a new volume after a change in temperature. So now that we're going to find a new. What is the new volume? The new volume should be V2. The initial volume is V1. Anything initial is either V1 or sub 1 of I, meaning initial. It could be V sub I, V1, it could be initial. It could be P sub I or P1, all right? And so on. So, or T sub I or T1. So here's the temperature factor. T2 over T1, temperature factor. You see, when you do with this factor, look at what you're trying to find. That should be in the numerator, all right? You're trying to find V2, so therefore T2 should be in the numerator. And V and T1 should be in the denominator. This is how you set up those factors. All right. So therefore, to find a new temperature after a change in the volume, so here's the factor. V2, all right? And T2 is what we're looking for, so therefore, you don't have that T up there, V2 up there. All right, so we can cross multiply. So here we go. 132 liter helium balloon is heated. From 20 degrees C to 40 degrees, that means from room temperature, we can heat it up, go past room temperature, which is 25, go above room temperature, and now we're way up to 40 degrees Celsius. What is the final volume at constant P? So keep that in mind. Bohr's law, temperature is what? It's constant. In Charles's law, pressure is constant. All right? So therefore, we first have to convert the temperature from Celsius to Kelvin. Kelvin is what? C plus 273. Now, when you get a Kelvin, you don't say degree Kelvin. You can't say that. Don't say that around anybody who into science. So just, we can say degrees Celsius, degree Fahrenheit. We cannot say degree Kelvin. Keep that in mind. So Celsius plus 273, which is the absolute system, we give you the 293. So the room temperature is 293 Kelvin. Somebody said 293 Kelvin, they're talking room temperature. All right. So therefore, we go into what? We change that to 313, which is 40 plus 273. So now we set this up. And what do you see there? You notice that the volume is 141. What do you start with? You start with 132. 132, and you start with temperature 20, right? Everything on the low side. But because the temperature went up, the volume also went up. So Charles was now able to make his presentation to the scientific community and say, I proved it, I got it. I demonstrated this to you using cryogenic system, which is a liquid nitrogen, and I've proven it to you that they go together. So therefore, you have a straight line. V over T, quotient, give it a straight line. Keep that going. So in 1802, John Gay-Lussac discovered that the pressure of a gas is directly proportional to the temperature in Kelvin. So Gay-Lussac said, okay, all right. I saw what he did. Boy, I saw what you did. Charles, I got something too. I got something. You got nothing that when a guy can do this thing. I can do it one myself. I'm going to show you a relationship between the pressure and temperature. And tell volume to go sit down. Go sit down, volume. You sit down this time. You've been around so long. Go sit down. So Gay-Lussac, so he said the P direct proportional to T. You see the straight line there? The minute you see straight line, you know that something divided by something. That should tell you something. So he got a straight line too, just like Charles got a straight line. Because Charles said what? V over T, and now he's gonna have what? P over T. So therefore, he's gonna get a straight line. So keep that in mind. Boyd didn't get a straight line. He got a curve, a hyperbola. All right. So therefore, we see we can write Gay-Lussac law as an equation using a proportionality constant K. P go to KT, P over T. So therefore, P1 over T1 is equal to P2. Again, you can cross multiply. You can say P1 times T2 or P2 times T1. You can do that. That's the best way to solve this problem. Do cross multiplication. So what did he do? What did he do to convince the scientists of what he was? So here's his experiment. Here's an illustration of Gay-Lussac law. As the temperature of a gas in a steel cylinder increases, as the temperature increases, so he kept watching the steel cylinder. The pressure increases. Wow. There's more bumping around. There's more collision. They hit it real fast. They're jumping around. They're jumping. Woo, they're jumping. He said, look at that. Isn't that something? There is more jumping going on. So he said there's more F for A going on here. You know? F for A, whatever. 4 divided by unit area. All right. So this was the way to convince the scientists. Scientists said, oh yeah, you got something. Yeah, all right. You sure got something. What your graph look like? Straight line. To find a new value after a change in temperature, we set up the T factor. That's a T factor there. To find a new temperature after, so you got, depending on what you're looking for. So therefore, you got a T factor, you got a P factor. So here's the problem now. The steel container of nitrous oxide at 10.4 atmosphere. That's the beginning of pressure. It's cool. Get that? It's cool from 33 degrees C to negative 23 degrees C. What is the final volume at constant V? All right, now we need to think about that problem. All right, so we see that change everything to what? To Kelvin. Change everything to Kelvin. That's the first thing you must do. When you deal with Charles' law, Gay-Lussac, you got to do what? Change everything to Kelvin. And so now we see that you start with what? 10.4. All right, what was the temperature? 33. And temperature, and so therefore you see the difference there. All right. So these are the things you got. So that'll give you the straight line. When we introduce boys, Charles, and Gay-Lussac law, we assume that one of the variables remain constant. Boyle's law, we said, well, temperature was what? Constant. Charles' law, we said what? Pressure was constant. And Gay-Lussac, we said volume was constant. So now, experimentally, all three temperature, pressure, and volume, PVT, the PVT system usually change. So here's what we're going to do. We're going to combine, all three laws into one called combined gas law. Pay attention to that. All right. You got P1V1 over T1. You got P2V2 over T2. Now let me show you. Let's find it. Let's find the three. If you cover T1, everybody should cover T1. You get what? PV. You get Boyle's law on the top. Everybody see that? You get PV. If I cover P, I got V over T. V over T. I get Charles's law. V over T. If I cover V, I got P over T. Did everybody see that? Can you all see that now? Who doesn't see it? Can you all see that? All three laws are right there. P1, V1, that's Boyle's law. P over T, Gay-Lussac, V over T, Charles's law. Combining all three laws into that. Because what? Experimentally, all three usually change. So now each guy did their own thing. So now we put them all together. Let's go call it combined gas law. All right. So here we go. To find a new volume where P and T change, you gotta manipulate the formula. Okay, take a look at that. If I multiply P1V1 by T2, I get P1V1 T2. This is a cross multiplication now. Whenever you have a quotient, these are both quotient. You need to do what? You need to consider cross multiplication. So multiply P2V2 by T1. So P1V1 T2 is equal to P2V2 and T1. So if I grab this piece right here, P1V1 over T1, what do you expect to get? You should have a straight line. All right. So here we go. So you got to be able to manipulate those variables in order to get what you want. So we got two factors. We're solving for V2. We got a pressure factor. We got the temperature factor. When we're solving for P2, we had the volume factor and the temperature factor. When we're solving for T2, we had the pressure factor and the volume factor. These are things that we passed earlier. All right, so they are seen within the combined gas law. All right. In a combined gas law problem, there are three variables: PVT, three variables, PVT. Let's apply the combined gas law to this problem. 10.0 liter of carbon dioxide, gas at 300 K, and 1 atmosphere. If the volume and Kelvin temperature double, what is the new pressure? So yeah, you got to set up a table like this. This is the best way to approach this problem. What are the conditions? The conditions will be initial and final. Initial and final. Those are the conditions. PVT, pressure, volume, temperature. Okay, so when you set up like this, then you try to substitute. Initially, they got what? 1 atmosphere. Okay. 10.0 liter for volume. All right. And the temperature is 300 Kelvin. That's initially. What are they looking for? They're looking for, the question says, if the volume of Kelvin temperature doubles, what is the new pressure? Look for P. So you see the volume was 10, now it's 20. The temperature was 300, now it's 600. Doubles. So the best way to see these conditions is to put it in a tabular form, in a table form. And you do that, you can see better. All right, so this is what I expect of you when you're doing a combined gas problem for that homework. I want to see this. Some say, oh. So this is what I'll be looking for. Now, so P2, you got a P1 times V1, the volume factor and the temperature factor. To have that. So this is how the problem should be set up. Vapor pressure. Oh, vapor pressure. You talk about vapor pressure in your last experiment. Is the pressure exerted by a gaseous vapor above a liquid when the rates of evaporation and condensation are equal? Let's talk about evaporation and condensation. Okay? So, we have what? We talk about the physical, these are all physical. Evaporation, condensation. So this is what I do when I make my mouthwash. The mouthwash that I make is done by the evaporation and condensation method. I take the cinnamon sticks, and then evaporation takes place, and then I condense it. So that is the condensate that we use as mouthwash. All right. So it says here evaporation and condensation. So we say freezing and melting. These are physical things that we talk about. And so vapor pressure increases as the temperature increases. So you boiling something. All right, it's liquid ethanol on an initial level. All right, just sitting there. It's evaporation very slow. But here, the final thing that happened here, and so what happened? Vapor pressure increased. So what you got more of this stuff coming out. So this is when you cooking anything. This is what happened. All right. So here we go. Dalton's law is coming up for lab. Pay attention to this. Is that John Dalton say, okay, I want to participate. I see Tarasella did his. I see Boyd did his. I see Charles did his. I see Gilliside did his. And now I want to take part. So that's what the law say. Partial pressure. Said that the total pressure of a gaseous mixture. You have gases mixed. Every gas in that mixture got its own pressure. It's equal to the sum of the individual pressures of each gas. Now, in chemical engineering, when we're doing distillation, there's some guy called Raoult's law. But Raoult deal with solutions. So therefore, P1 for that gas, P2 for another gas, P3 for another gas. You put them all together. All the gases in that container have a total pressure. So the total pressure in that container is based on the contribution of each gas in terms of the pressure that they provide. So the pressure exerted by each gas in the mixture is its partial pressure. The total pressure is putting them all together. That's Dalton's law. This is the experiment you're going to be doing. It's coming up soon. It's not too far away from you. Today you're doing Charles's law. We're talking about Charles already. For those of you this morning, you already did. And for those this afternoon, you're going to be doing. Anybody have a question?
Yes, please. For the equation, how it says pressure 1, pressure 2, pressure 3 equals pressure total. Does that mean like if it were just those three, it would be pressure 6?
Huh?
The equation,
Oh, no, they're just trying to identify the gas 1, gas 2, and gas 3. That's all.
Okay.
Yeah.
Okay.
Yeah. Good question. A sample of noble gases. You know what noble gases on column 18? You know that? We talk about those on the periodic table. A sample of noble gases contains what? Helium, neon, argon, and krypton. So they all, that's a sample. You have a sample, and it has helium in it, has neon there, it has argon, krypton. All right? So therefore, what's going on? If the partial pressure of helium is what? 125 mm of mercury, neon. But if I were to give you problem in terms of Boyle's law, Dalton's law, I will have you solve the pressure first. I will not give you a list. Let me give it to you. This is cheap, very, very cheap. All right. But I won't give it to you like this. I'll make sure that you solve for the pressure first before you add them up. That's touch of him. All right. So what is the total pressure of the sample? So you add them up. Helium got his pressure. Neon got his pressure. Argon got a pressure. Krypton got a pressure. Put them all together. You have a total pressure in that container. It's just very simple. Not that difficult. All right. We can measure the volume of a gas by displacement. We talked about that before. All right. So we have here, take a look at the experiment. We used to do that a lot in the lab. Okay. So by collecting the gas in the graduated cylinder, so you fill the gas, you fill the graduated cylinder with water, and then you take, the gas, and the gas will display the liquid in the graduated cylinder. You can't see the gas. So we can see where there's no water, that area would know now it is where the gas is located, even though we can't, unless we color the gas to see. But we can see now that where there's no water in the graduated cylinder, that area is hydrogen gas and the water vapor. Water vapor, all right? That means it has water in there. Okay, gas. The gas collector is referred to as wet gas, so therefore it's considered wet gas, since it also contains water vapor. Okay, so that's one thing, something we do in the lab setting. And ideal gas, let's talk about ideal gas. Ideal gas is be perfect. Perfect. All right? We assume that. They will be perfect. Nothing is perfect. You better believe that. We are not perfect. We don't expect for gas to be perfect. But we need to predict that behavior. What if it was perfect? Let's solve the problem based on the fact that it is perfect. This is where the Avogadro come in. Avogadro want to get into the system. So now, we're gonna use the Avogadro concept here. So an ideal gas is a gas that behaves in a predictable and consistent manner. Ideal gases have the following properties. So to be ideal, to be perfect, this is what must go on to be perfect. None of us are perfect. I'm talking to you now, I'm not perfect. And you're not perfect either. Nobody is perfect. But what could we do to be perfect? What could we do? What are some things that we must do to bring the perfection? So for a gas to be perfect, here are a list of things that the gas must possess to be perfect. Otherwise, it's a real gas. So we are assuming this. Talk about predictability. We talk about that. We say in science we are predicting. Predict. And I mentioned that we have three ways we can do prediction. Remember that? I hope you got it somewhere in your notes. Repetition, It's the simplest form of prediction. Interpolation, extrapolation. You still remember those things? Oh, one day I'm gonna see you in the street. I said, let me see your notes, huh? How about that? All right. So, in order for a gas to be perfect, the gases are made up of tiny molecules. Are the gases made of tiny molecules? Gas molecules demonstrate rapid motion in straight lines, not in curves, and travel in random direction. Randomly. Gas molecules have no attraction for one another. Mind your own business. Don't touch somebody. Keep on going. Keep going. Otherwise, you're not going to be perfect. Do not touch. Gas molecules collide without losing energy. They collide. They still got the same energy. Just roaming around, having fun. They say, oh, I'm tired. Oh, boy. I've been colliding all day. I'm so tired. Man, hey, brother molecule. Aren't you tired? I'm tired, man. I'm tired. Oh, you're not going to be ideal. You're not going to be ideal. You better quit saying that. You better quit saying that. You're not going to be ideal. You want to be ideal? Keep on going. Don't lose that energy. Keep on going. You want to be ideal? Keep on going. Average kinetic energy. That's what temperature is all about. Average kinetic energy. We'll talk about one continuum with a bunch of molecules. If you have a cup of hot water, boil water, and in a teaspoon, you got the same water in there, hot water. The temperature will be the same. But which one has more heat? You know, remember that? Way back there? I'm taking you back now. The cup has more, we got more molecules in the cup. And the teaspoon has less heat because what? Fewer molecules in there. So the average, so the temperature is the average. So we take the temperature, out of all the molecules in a teaspoon and get an average. Out of all the molecules in a teacup, get an average. So that's what temperature is about. That's why heat and temperature are not the same. So the average kinetic energy of gas molecule is proportional to the Kelvin temperature. That is KE directly proportional to temperature. So to be the ideal, it's a predictability that we're talking about here. To be ideal, these are the things that you must have. Do you want to be perfect? Any of you?
No mustard, no mayo, no double meat, no cheese.
No, because I was going to ask about the whole like what do you want on it? But they're like,
why didn't you call me before you got there?
That's also true.
You're not muted.
Yeah, I should have.
Are you finished now? It's my turn. All right. So we say here, the average kinetic energy of gas molecule is proportional to the Kelvin temperature, that is a KE, so therefore we say. Now, these are the things that you gotta have to be ideal. Let's go right again. Gases are made up of tiny molecules. Are you made out of tiny molecules? Gas molecules demonstrate rapid motion in straight lines.
Yes, sir. I mean, we have stuff.
And travel in random direction. Gas molecules have no attraction for one another. Gas molecules collide without losing energy. So these are the things here. So here's, now, remember I talked to you about extrapolation? Here's an example of an extrapolation. The highest form of prediction. So temperature where the pressure and volume of the gas theoretically reaches zero is absolute zero. So here we have the points here. We do the experiment and the point stops here. So we are saying to ourselves, if we continue to do that, we can hit that zero. That's zero. That's the those dotted lines that fall. That's what we call extrapolating. Extrapolating, we predicting that we could reach that point. That's extrapolation. That's the highest form of prediction. If we extrapolate T versus P or T versus V graph to zero pressure or volume, the temperature is zero. Kelvin, negative 273 degrees. So that's extrapolating. All right. Now, recall. I mean, we talked about it before. Recall that the pressure of the gas is inversely proportional to volume and directly proportional to the temperature, the number of molecules. So P, the NT, the N there, number of moles, the Avogadro now, NT over V. T over V, that will be Charles's law. All right. So if we introduce a proportionality constant, R, gas constant, we can write the equation P equal to RNT over V. And now we can have PV equal to nRT. That is the formula for ideal gases. To be ideal, you have a list of things that a gas must have in terms of property to be an ideal. So we assume, all right? Now your textbook does not talk too much about real gases. Real gases, we have van der Waals, higher level will give it. So if we do the van der Waals correction, so it'll be P plus A over V squared equal to V minus B. That's the correction factor for volume. All right, well, all those are none there, then we have PV equal to nRT. But don't worry about what I just gave you. But just worry about PV equal to nRT. Very important. This is the ideal gas law. The constant R is the ideal gas constant. It has a volume of 0.0821. Now, the easier way to remember this constant is to say August 21st. August 21st. 08, that's August, 21 is August 21st. So easier was August 21st. All right, easier way to remember that constant. How many moles? Sure. Go back. No, you need to have a constant written on a sheet of paper. I'm not there, but make sure you write them down, right? Now, in a normal situation, I would say before we start the test, I'll go around checking all your notes to see what you got written down, what not supposed to be there. You know, I would check for the constant, but I'm not there. So I'm leaving it up to you to make sure you have that. All right. So now, to solve for N, we say what? How many moles, mole N, of neon gas occupy 2.34 liters at STP? Remember that STP? Standard temperature pressure we talk about? 0 degree, 22.4 liters, 1 atmosphere. It's still following with the many year STP. That should register in your mind. All right. 0 degree in Kelvin is 273. All right. 0 degrees C is 273 Kelvin. The pressure is 1 atmosphere, and so on. Rearrange the ideal gas equation to solve for moles. So that's, you rearrange PV equal to nRT, isolate N to solve for this. So and make sure when you're solving these problems, pay attention. Keep the units in the problem. So I want to see which unit will drop out. Now, if you send your homework to me and just put a number with no unit in it, I'm not going to take it. So I'm letting you know now. Keep the unit, the desired unit will remain. After you do all the cancellation, the unit we need will remain. I want to see that unit that will remain. All right. So regardless of temperature, all gases are randomly distributed in their container. However, the average speed of gas molecules changes with temperature. This is true for all gases. All right. Gases have variable shape and volume. The pressure of a gas is directly proportional to the temperature. and the number of moles present. The pressure of a gas is inversely proportional to the volume it occupies. Standard temperature and pressure are exactly 1 atmosphere and so on, okay? So Boyle's law, you got Boyle's law there, where temperature is constant, and we have a curve, we have a parabola, a satellite dish on top of your house. Charles's law is a quotient. We have a straight line. Gay-Lussac law, we have a straight line. Combined gas law, we have a straight line because you have that's something over that. Divide by that. All right. So Dalton's law, the pressure for gas 1, pressure for gas 2, pressure for gas 3, give it to the pressure. Ideal gas law. So these are formulas you need to have for yourself on the exam. If you can't remember these formulas, have these formulas with you taking the exam. Not your textbook, but just have it on a sheet of paper, the formula will be there. The ideal gas law is PV with NRT, you have that on your formula. The gas constant, you can remember it, August 21, liter atmosphere per mole Kelvin. All right, so there you have it. Any questions so far?
Professor?
Yeah?
My name wasn't called during roll earlier.
Just a second.
Okay.
Let me see now. We have one name missing here. What group are you in?
I'm in group 10.
Group 10?
Yeah, my last name is Teodoro.
Oh, your name is not even on this list. Group 10.
Or I'm in group 11.
11? No, 11. We got 10.
She's in group 10.
She's in group 10?
Yeah, my last name is Teo.
Hold on for a second. So now you're in group 10, okay?
Oh, yeah.
Okay, what's your first name?
Reja.
Reja.
Yeah, and that's it.
Uh-huh. And the last name?
Teo.
Teo.
Oro.
Teo what?
Teo. D. ORO.
Torl. So that Torl.
Oh, it's Teodoro.
Well, spell it again.
Okay. Teo.
Yeah, I got
D.
that.
D as in dog.
Oh, D. Okay.
Yeah.
Okay. Uh-huh.
O.
Mm-hmm.
R.
Mm-hmm.
O.
Doro.
Yeah.
Okay. Teodoro. Okay,
Yeah.
so I have you now. You remember you're in group 10.
Yeah, I know. Thank you.
All right. Now, one person that didn't in group. Let me see that group there. Group 9. One person was missing. The last name is Bulosan. That person is absent today. Okay.
Professor, this is Jason Calderon. Did you include me for the roll call for today?
What group are you
in? Group 3.
Group 3. Jason, no, I didn't. Okay, Jason, I got you now.
Okay, thank you.
Okay. All right. So that person in group 9 is absent today. So everybody should remember now, I'll call roll every day. Okay. So, because you know you get your points from, you got, how many points do you get from, how many credit do you have? You get, let me tell you what you get. Now we're going for the exam. Tomorrow is our last lecture before the midterm. And so,
Professor, sorry, I have a quick question about the midterm. I'm not sure if you already had answered this. I know we have how many days, but how long exactly are you allotting us like hours to complete?
once you complete it, that's, if you could, you have, it starts Thursday, right?
No. What I'm saying is how many hours are you allotting us to complete it? So like when you start to finish, so is it like
1.5 hours?
1.5? Okay, thank you.
1.5 hours. Okay, so
Yeah,
you
so-
got.
And also, really quick, what day are we given for the test? Like, is there a specific day that we have?
It starts on Thursday.
But is that what day any of us get to start?
On the 30th.
All of us can start that day, though.
Yeah, everybody.
Okay.
Yeah. Okay, so you got attendance. It's 50 points. All right, that's a lot of points. So make sure you're present every day, so you can't lose out on the 50 points. The final exam is 200 points. The exam you're going to be taking now is 150 points. Homework should be coming in by Thursday. Want to get the homework by Thursday, and that's order the homework from 1 to 11 should be in. The rest of the homework will come in on the day of final. So homework should come in on by Thursday. Lab report are coming in. I'm collecting the lab report. So that's make sure your name is on the people that are in my lab, because not everybody in my lab. I'm talking about people that are in my lab. So make sure you have your name on the lab report, okay? And so if you don't have any question, I'll let you go for the day. So you go and do some work, okay? Do you have any question from previous lesson? I can go there if you have a question. If not, I'll see you tomorrow. We'll be doing liquid and solid tomorrow, okay? Is that okay with everybody?
Thank you so much.
All right. Be on time.
Have a good evening.
Good
morning.
Sorry.
And drive safely, okay?
Yeah, bye-bye.
All right, bye-bye.
Professor?
Yeah?
Sorry, on Thursday, I know that's when our midterm we can start. However, do we still have class that day or no?
No, we don't have class.
No class. Okay.
I'll be grading. I want to be grading the homework, So turning the homework
So just
on
turn
that
it
day.
on Thursday, but no class. And neither for lab, no lab either?
No, there's lab.
Oh, there will be lab. Okay.
Yeah. Mm-hmm.
Thank you.
All right. You take care. Well, everything will cover. Everything you got to do calculation, something, a lot of calculations. But just have the formulas with you and read the question carefully. Yeah. All right. Anybody else?
Yeah, Professor. Did you say in one of our other classes that the total number of questions will be like around 15 for the midterm?
15 something, 10 to 50. Yeah.
Okay. Thank you.
Okay.
Thank you.
All right. For 1.5 hours. Unless you're an SPS student, it'll be more. Okay. All right. I'll talk to you later.